Yeah, good morning. In this session, I would like to demonstrate the use of optimization toolbox in Aspen. As you can see from this problem statement, propane need to be compressed from 14.7 to 120 psi with two single-stage polished tropic compressors separated by a cooler that reduces the first compressor outlet temperature to 1. Develop an optimization that will select the outlet pressure of the first compressor such that the work required for the system is minimized. So let us try to see how to simulate this problem in Aspen. So we are using only one component, propane, in this problem. So define the component, select a property model. So typically when the pressure is high, be careful in selecting appropriate property model. So let me choose PSRK. Next, go to simulation environment. So we are using two compressors separated by a cooler. Let me use a cooler, connect the input and outputs. And define the problem statement. So let me choose. So the feed propane is entering at the rate of at a temperature of 200.7 psi and with a flow rate of 5 lb/moles per hour. We have specified the input stream. Now we need to specify the block. The first compressor, we have given that it is isentropic using ASME method. Isentropic efficiency is given to be 0.72 and the mechanical 1 in the problem statement. So we need to compress propane from 14.7 to 120 psi. So we don't know what is the intermediate pressure or the exit pressure from the first compressor. Use this to be 50, a random guess. Anyway, we need to find out the optimal pressure at the exit of the first compressor in order to minimize the total work of these two compressors. This is also isentropic. The efficiencies are similar to the first, 0.72, and mechanical efficiency is 1. If you don't provide these, Aspen will be using some other values. And the discharge pressure, we know clearly that it should be at 120. We have defined both the compressors. Now we need to define the heater. So the outlet temperature of the heater is 2 heat. Let us presume that there is no pressure drop across the heater. So we have specified all the required input. So we should be able to run our simulation. Now you can see, of course, the output is at 120 psi, the required pressure, but the pressure is at 200. When it is compressed from 50 to 120, the temperature increased to 279. That's one issue. Similarly, if you look at the first compressor, so this, when you increase the pressure from 14.7 to 50, the temperature increased to 309, and this 309 was reduced to 200 by using the heater block. Anyway, let us have a look at the work requirements in both the compressors. So this is 4.6428 HP. If you want, you can change the units and observe. Similarly, the second one requires about 3.14, 4.6 and 3.14, roughly about 7.7 or so. But is this the minimum work? So now we are required to use an optimization toolbox in order to minimize the total work that is required. So go to Model Analysis Tools, expand and click on Optimization, say New. Okay. Now try to define all the variables that are involved in the objective function. We need to minimize the sum of the works required by both the compressors. So let me define network in the first compressor, a block variable. Block is B1. Right? Let us say in HP. Similarly, network of the second compressor. This is also a block variable. Block is, I think, B2. Yeah, B2 is the compressor. B2 variable is network. So let us define our objective function. We need to minimize the sum networks. Constraint. In this problem, it's an unconstrained problem. We wanted to minimize the total work required by both the compressors in order to achieve the required compression. But what is that we are trying to vary? We would like to find out the optimum pressure at the exit of the first reactor. So we would like to vary the block variable. Block is B1, variable is pressure. Specified outlet pressure. Initially, we assumed this as 50. Right. So we don't know. 14.7 is the inlet. So let me assume that it is somewhere between 20 and 120. Right. So let us run the problem. So as you can see, the simulator by default will be using this algorithm, sequential quadratic programming. So it took about 8 iterations before we can finalize, before we can get to the required solution. These are the initial values, the network required when we started with the initial run. Now the amount of work required, objective function, is 7.76. In fact, we were very close to that value even in the beginning because probably the manipulated variable, that is, started with 50 and the optimal pressure at the exit of the first 41, we will be able to minimize the total work required. Of course, in this example, you have seen a problem, optimization problem, which is unconstrained. In fact, in one of the other problems, especially the reactor problem, two CSTRs connected in series, we have seen a constrained optimization problem. So let me close the session with this.